Thank you.
Thanks for the introduction. Thank you all for attending. So at some point I realized that there is no notion of Git anywhere throughout my slides. It's something called like curse of knowledge, as I learned it on the talk about documentation. So yes, I'm going to talk about Git and how we're going to revert merges in Git. Well, first of all, who's using Git? Oh, that's great. That's the proper audience. Yeah, so, great. So let me start with a little story that might demonstrate how actually Git works in the big companies. Well, it is me. I'm sitting doing some programming stuff, like usual, everything's good. And at some point I receive a notification from Outlook that daily health check have failed. Okay, that's not a problem. Most probably the responsible guy is already aware of the problem and is currently fixing it. And then at some point, the junior guy appears. And he says, hey, seems like I've done the wrong merge. Okay, I can clearly see that. Well, if you done the wrong merge and you cannot fix it right away, and you cannot push the changes to fix the build directly, you can simply revert it just to make the build green again, and then you revoke your changes and merge it back again. Yeah, you know about that. You see, actually, I already reverted the merge. Really? So, but the build is still red. So how did you actually reverted it? So that's how it usually happens. And if such thing happen, this is usually a beginning of a mess. So let me continue. First of all, a little Git 101. Just the bare minimum of the theory you must know to be able to understand the rest of the talk. And the big disclaimer, that's not how it actually works inside Git. That's not how it is stored inside Git. This is just simply a mental model that you need to keep in mind to be able to reason about almost everything you will ever need in Git. So this is just a mental model. This is a commit, right? Commit has a header. Header contains author. It contains committer. It contains date of the commit and commit message, etc. Then we have a hash, and each commit have a unique hash. And you can uniquely identify this particular commit by the hash and nothing else. So the hash is a unique identifier. It's very important. And of course, commit contains the actual change set. That's what the changes you introduce to your code base with this commit. Okay. Then you have a list of parents. By list of parents, I mean the list of hashes of the commits that are parents of this particular commit. Usually, commit has only one parent, and this is a regular commit. It can have more than one parent, and this will be a merge commit. Usually merge commits have two parents, but generally a commit may have any number of parents. And raise your hand if you already did know that. Okay, great, several hands. Also commit can have zero parents, and in this case commit will be root of the repository. Usually your repository have only one root. It's at the beginning of the repository. But generally a repository may have arbitrary number of roots. And raise your hand if you already knew that. Okay, approximately the same hands. Great. Another concept we need to know about is, of course, branches. So Git has branches, and branches in Git are a very lightweight concept. Branch is simply a reference to a commit, and by reference I mean, of course, the hash of this commit and the name. Something more, but it's not important for us. So in the scope of this talk, I'm not going to explore all the mess with locals and remotes and conflicts and all the other stuff. So this is the whole theory we actually will need to understand what are merges and how we can revert them and what are the implications. Okay, so let's merge something already. If we want to merge something, we need a branch. So let's have a branch. We have our branch dev. While we have our branch, some work is being done on master. We have new commit B and new commit C. That's how master evolved. Then we make changes to our branch. So we have commits D and E on our branch. Then at some point we realize, hey, our work is done. We need to share it with the world so that everyone can experience the awesomeness we invented, right? So we check out master, and then we merge dev into master, like the usual workflow, like this. So I assume most of you already did something like this in your life if you're using Git, correct? Then at some point, when we no longer need dev branch, and dev branch is already merged, we don't actually need this anymore. At some point, branches that are merged are usually pruned in your repository so we can safely delete it, because the information is already saved. And that's what you have in history after some point in time. That's how it will look. Now, imagine the second step. That's me. I'm back from vacation. I'm happy, and I didn't pull for a while. That's what I see. Just an old state of the commit. And then some team lead appears and he says, you know, there is a guy who actually pushed the wrong merge and it seems like it doesn't work and everything failed. So could you please revert it? Like, okay, no problem. I did it like 1,000 times. Why not? So let me pull first to see what's happening. I'm pulling, and that's what I see. Okay, great. I see the merge. I see the commits, and I realize, okay, I need to revert it, right? So what I need to do is to revert the changes introduced by commits D and E, right? Wait a little. Or maybe I need to revert the changes introduced by commits B and C. How do I know? Because I don't even see dev branch. It was already deleted. How? No, actually, how do I know? Reflog. What? The suggestion is to use reflog. What are you going to see in reflog? Okay, good point. So the observation is that you can check out the reflog and see where the master was pointing to. I'm not actually sure that Git will provide me such information in this case. I'm not sure. But the point is that usually, if you're a user of Git, you use some indirect properties of the repository. For example, you see that merge was done by Petya, right? So most probably the work he was merging was also committed by the same Petya. And you see if commits D and E are made some Petya. So probably this is what we're going to revert. But that's not always the case, right? You also may suggest that most probably on master branch, there are much more commits than on the dev branch, because on master branch, the whole team worked, while on dev branch, only Petya worked. But this is, this is not always correct too. So you cannot be absolutely sure. And generally, there is no way to know. Because Git doesn't remember on which branch a commit was made. So generally, we cannot do it. But there is a useful convention that you should actually be using also. So first of all, one thing that we need to know is that parents of commit in Git are ordered. So we have first parent and we have second parent. Let's say about merges with two parents, of course. And Git guarantees that first parent corresponds to the commit that was on the branch we were merging into. And the second commit, what was on the branch that we were merged from. So here we see that the first parent is C, it was on branch master, and we was merging into master, and the second is on commit E, which was on branch dev, and we were merging from dev. And now the convention is that first parent always corresponds to your main line. It corresponds to the master or active or trunk or release or whatever you are using for your main branch. This is the convention. Now, let me elaborate why this is a convention. Because let's go back in time a little bit. That's how our repository look before the merge, right? And then imagine that we are not ready to immediately merge into master. We first want to merge master into dev, do some tests, resolve commits, if any, and spend some time investigating that this is okay. So we're creating a merge commit in dev branch. We checked our dev branch and merged master into our dev branch. In this case, according to the order of commits, E will be the first commit, because this was on the branch we're merging into, and C will be on the second parent. Okay, so we investigated our current state, tests are good, everything looks good. Okay, we're ready to merge back into master. So what we're doing, as usual, we're checking out master, and then we merge dev into master. And that's how it might look. What happened here is fast forward. So this is the merge strategy that Git implements by default. If there are no more commits on master branch here, if C is the latest commit, we made branch and we quickly checked out that everything's fine, and then we merging back. Chances are there are no new commits on master. And in this case, the merge will be fast forwarded. So Git will not create new commit unless you explicitly told him to do this. And that's how it looks. And of course, after some point in time, dev branch is already merged, so we got rid of it, right? And that's what we see. And now let's compare what we have. So we might end up in two almost identical situations. And the only difference will be in the order of commits, in the order of parents of the merge commit, M and M prime in this case. So the convention is you're not doing the second picture. The convention is you're doing the first picture. So at this point, let me illustrate it with some demo. Okay, so here we have our repository. We have master branch, and we have commits B and C on the master branch, and we have dev branch, and we have commits D and E on the dev branch. For convenience, each commit has only one change. Each commit adds a file with the corresponding name. So commit A adds file A, commits B adds file B, like this. Let's see, this is file C, etc. Okay, so let's do the first scenario, the usual and the recommended approach, the conventional one. We're merging dev into master. So we select dev and we click merge. Now let's see what happens. Here's the state of the working repository after merge. We have files D and E which correspond to commits D and E. So this is very logical because D and E was what was our work on dev branch, and we're merging it into master. Great, that's what we need. Okay, so let's call it M, right? Now we have commit M, merge commit. Yeah, that's great. So let's leave a tag here because we will need it later. That's the first case, that's the upper picture. That's what you usually want to do. Now let's go back in time a little bit. Let's reset master to where it were, like this, pretend nothing happened. Now, the second approach. Now we check out dev first, it's our dev branch. Then we merge master into our dev branch, just to do some testing. And that's what we see. Now we have commits B and C merged, because these are commits that were on the master branch, right? We merged them into our dev branch. Okay, great. Now let's commit. This is called M prime. And now look how it is drawn in the client. And every client will draw you the same thing. Now Git thinks that the main line is actually D and E for commit M prime. So now let's, when we created a merge, and we tested it and everything looks fine, and then we are ready to merge dev back into master, right? Okay, so we're checking out master, check out, and then we're merging dev. So the client is smart enough to understand, and this is a special situation when we can do a fast forward merge. And it explicitly asks us, do we really want to do fast forward or not? Okay, yeah. Let's stick to the default. Let's do fast forward. And that's what we have in this case, the master branch and M prime commit. So you see how the client also doesn't know which commits are on main line. So it follows the same convention. It assumes that whichever is on the first parent must have been the main line. And that's how it will draw it. Now, if we show commit M that we've done before, now you see how it reads that commits B and C on the main line. But these commits are almost identical. They merge commits with the same parents. Okay, so that's clear. Now let's check out where it were, how it should have been done. Let's go back time a little bit. Okay, now we have our merge commit, the proper one. So that's yeah. Now that we understand that for merge commits, the parents are somewhat relative, that might be in every order. Now at this point, we're actually ready to revert the merge. So okay, let's revert it. And it asks us, and if you're using console, it will require you to specify additional argument -m or something. So it asks us, okay, which commit actually correspond to the main line? And we're saying, well, C. It's C, right? Okay. And then what we are reverting are D and E, because D and E was on that dev branch that we are going to revert, right? So imagine we did it differently. So let's abort for a little bit. Let's do not revert. And let's revert again, and let's pick the different main line, as if master was on commit E, as if. And let's see what happened. Well, in this case, it reverts a different branch. In this case, it reverts, well, we don't actually see. So look at the right one. Sorry, you don't see that there are B and C there. Let me try to 8. Well, now you see it. Sorry. Why didn't everyone complain? So now we see that commits B and C were actually removed with the revert. Well, that's not what we want. This is just to demonstrate what happens. Let's abort and let's do the revert properly from the correct parent C. And now we see that D and E are removed. Okay, and let's call it hat M. And this is how we revert the merge. So when you need to revert a merge, you just need to choose your path. So it's pretty much it, but we seems like we have some spare minutes left. So let's call how can we continue living after the revert? Because you see, at some point, most probably you decide the changes you were making on dev branch, they are not useless. You want to merge them somehow. So first of all, you want to fix them. Are we fixing them? So pretend commit F fixes everything, all the errors that you have. And then you're trying to merge it again, like this. Well, it's pretty straightforward, right? So you fix your dev branch, then you merge it again. Well, it won't work. Because this will only merge changes from commit F. Who understands why? Okay, I see one hand, two hands. Great. Because you see, you need to understand what merge is. And the merging from dev branch to master branch is actually the same thing as saying, I want every commit that are on dev branch, but are not on master branch. But let's take a look. Commits D and E are already on master branch because we can reach them from master because we already merged them, and it doesn't matter that we reverted the merge, because from Git's point of view, reverting is just a usual commit. So we reverted the changes, but we cannot revert the history. And the history says that commits D and E are already merged. That's why Git thinks that F is actually the only new commit that appeared here, right? So that's not what we want. We want to merge everything back again. So the question is, how are we going to merge this? Okay, there are actually several approaches, and I will demonstrate all of them. So the first one is we already know how to bring changes from commit F in our branch, right? So the question is, how do we bring commits D and E back into our working branch? Well, let's remember, we already brought them into master by M, then we brought them that we removed them by commit hat M, then we want to bring them back again. Well, the obvious thing, let's just revert the revert, right? Why not? Well, yeah, what can possibly go wrong? So revert M is actually, from the master's point of view, the same thing as M itself. And that's how we can do it. And now we're ready to merge. At this point, changes from commit F are merged directly by this merge commit, and changes from commits D and E are reintroduced by reverting the revert of the merge. And it works. It's perfectly fine. It has some pros, because you're not duplicated anything using the same commits D and E, and except for this mess in the master, well, sorry for that. But it creates somewhat complicated history because it's not quite easy to understand what happens here. So you have another approach. Well, let's go back to point in time just after the revert. And in this point, we just need to understand that it is time to move on. We need to abandon our current dev branch, and we need to create a new dev branch. And to make it all anew. And we need to, we can actually cherry pick all the commits from the old branch to the new branch. And this will create duplicates of the commits. So we have a new branch with the duplicated commits. And we have commit F that fixes everything, right? And at this point, we're ready to merge, like this. So again, this is the usual workflow. So from this point of view, we abandon this branch. We don't want to deal with this mess of merging and reverting and stuff. We're just doing it all anew. So it's like a regular workflow, which is quite convenient. The problem is we're actually duplicating commits D and E. And if you had, for example, your code reviews attached to those commits D and E, they won't realize that there are new commits D and E that are actually the same. Okay, and there is a hybrid approach. When you're sticking again to the usual workflow, but instead of duplicating commits D and E, did you remember how we brought commits D and E back into master the first time? We reverted the revert, right? So let's create dev branch and do revert of the revert on the dev branch. This is essentially the same thing as duplicating commits D and E, because that's what revert of the revert contains. And after that, we're making our commit that fixes everything. And after that point, we're ready to merge. So the hybrid approach is better in the sense that if you have some, if you had some conflicts resolution in commit M at this point, all these conflicts resolution will be preserved in this revert of the revert. If you cherry pick the old commits, you will have the same conflicts again, because these are exactly the same commits as before. But here you're reverting of what you have already resolved. So this is better in the presence of any conflicts that you had in a merge commit. You don't usually have conflicts. So if this is not the case, maybe this is not the proper approach. So yeah, one more wisdom. It's about how we do in the revert. Okay, and with the final word, I just want to say that there is another completely opposite technique to recover from the faulty merge, and it's done like this. Yep, simply reset master and force push. Yeah, that's all. But to understand all the consequences that you might have with this, we need much more theory than I introduced in the beginning of this talk. So I'm not going to cover this in deep details. Just want to say that if you have a small team, and if you immediately realize the problem, and if you have ability to help the users that might have problems of the force push, for example, you are the only owner of the repository, and I would recommend to use force with lease instead of ---- force, and go to the internet and read all the related details. So I just want to make you know that sometimes it is an option. And we actually did this once in our company with hundreds of developers, and it worked. It was awesome. Okay, so if you want to reset, of course, use the force, right? But with lease. Okay, so at this point, I hope you learned how to revert the merge. Thank you. If there are any questions.
Thanks a lot, and that's great talk. Thank you. And because I just see in my practice that a lot of people do not really realize what's happening under the hood, and that brings a lot of complications and time-consuming things. Okay, questions?
Yep. Background.
How's the client app actually called? You never named it.
What again, sorry?
The client application which you're using, you never named it. How it's
actually
called?
Yeah, because I didn't want it to seem like an advertisement. It's called Smart Git.
Okay.
Pretty awesome, I recommend
Thank
it.
you. So one more question somewhere here.
So one of the tasks you mentioned is finding out which branch was master. But if you have a system of continuous integration, you always know because it pulls each master commit, and you can refer to the continuous integration system and find out. So you can do it this way, right?
How about pull requests?
There are two questions. Sorry, I will answer the first. The first question, if I understand correctly, if you have a continuous integration system and you have a master branch, the continuous integration system always knows what it is pulling, right? Well, that's exactly the case I was showing when I was going back from my vacation. So I am the continuous integration system. And that's what I see. Then I'm doing the pull. And that's what I see. So which commits were where?
It uses Git hooks. Actually, a normal continuous integration system uses Git hooks, and each commit to the master branch is pulled. So each commit is stored in continuous integration system like Gerrit, etc.
So you assume that continuous integration, well, it must know that something have been pushed, but it cannot possibly know it before it was actually pushed, right? You mean pre-commit hooks or post-commit hooks?
Post-commit.
Post-commit hooks. So how can post-commit hook possibly know that I pushed something until I pushed it?
Okay, I got it.
Thank
Okay.
you.
I believe that, yeah. Mm-hmm.
Okay, thank you. And can the pull request mechanism block this problem? Let's start.
Yeah, good question. With pull requests, we are sticking to the policy, because when pull requests are approved, they make a merge, and merge follows this policy. So yeah, with pull requests, usually you have restricted like tree of your history, and usually things are easier with pull requests. They are not that flexible, and several scenarios are more complicated. But because of thanks to this restriction, it is easier. Yes. So good question.
Thank you. Any other questions? Okay, so let's thank the speaker and
Thank you.
we have a